Okay, today is lesson 6 in topic 3. You're going to want your Chromebook. You're going to want your book open to page 126. I believe it's going to be right around there anyway. And then have your calculator out. Also, we'll be using all of those. So first it starts off and it says a scatter plot. We've been doing scatter plots. Shows the number of beachgoers each day for the first 6 days of July. The head lifeguard at the beach uses the data to determine the number of lifeguards to schedule based on the weather forecast. So always look to see what your graph has first. So notice here we have that our x value are degrees above 80. Not the degrees exactly, but above 80. So that makes a difference. Pay attention to that. And then the number of beachgoers is right here. And what they want us to do is they took these two models. They must have done a trend line, whatever they did. We'll talk about that in a bit. But we're going to graph each of these. So right now, pause yours. And you can do this lots of different ways. You might be able to just use the y-intercept and the slope. Although 13, let's look at what every line is. That's 10, 20, 30, then 50, 60, 70, 80. Nope. So what is this? 10. So I figured out that 0 to 50, okay, halfway in between is 25. So then this line right here is 12.5. Not going to be real helpful with slope and y-intercept. So just make tables on those. So pause and come over here and make a table for g of x. Here's g of x. Well, actually, it would be right here. This would be g of x because that's our y value. And this is x. And then you have an h of x. Okay, so pause those. Come over here and do an x and an h of x. Find out just 3 values. Just plug in, well, we're going to plug in like 1 and maybe 5 and maybe 10. Do something like that because it'll make it lots easier to plot. Although each one of these lines is worth 1. So pick 1 to 10. Pick like 3 values and figure out a line. Go. So I came over here and I made tables for h of x and g of x. And I wanted to do them in different colors so you could see. So if I'm going to graph this one, it is 1 and 38. So you're going to have to approximate. There's 12, there's 37, so it's just right above that. And then we have 5 and 90. So 90, there's 75, there's 100, I don't know, someplace around there. And then we had 10 and 155, so just right above there. So that line, this is where, if you're in your book, take a straight edge so that you can actually see what is happening. Okay, there's one line. Okay, now let's do the other one. And so we have 1 and 42. Well, that's about the same place. And then wasn't this weird? Look at this freaky thing here. And at first I was like, did I do that wrong? Nope. I look back at the equation, you can see what happens. So 5 and 90 is actually the same. And then 10 and 150. So it's just right there. These are both really good lines. Okay. And we could come close, but neither one of them is exact, is it? So what is a reasonable domain? Remember domain, those are your x values. What x values could I plug in? We can kind of see from our tables what we did. We didn't go with a negative number because we're degrees above 80. Well, we're not going to go negative. That would just be that it'd be less than 80. So that's probably not going to, that's not what they're looking for here. So we're not even going to worry about that. We could, but we don't need to. So we're going to go from 0 on up. Okay, so we're going to go, well, let's write an interval notation. That would be 0, comma, but 0 can be included, so that's a square bracket, and then it just keeps on going. Well, except for, does it go forever and ever and ever? No, because above 80, well, if we go 20 degrees above 80, that's 100. So we could go 20. What about 30? That's 110. Yeah, that would still be okay, depending on where we at. In what state? Well, we don't know. So, it could get up that high. But if we did 30 degrees, 120 degrees, no, we're not going to do that. I mean, 30 would be 110. So let's just say 30 and just kind of cap it out right there. Okay, so we could go 30 above and still be reasonable because 30 above 80 is 110. Somebody might still go to the beach. Okay, so that could be our domain. And I did an explanation as we were talking about it. But you can see our trend lines. Remember, these green and purple lines are called trend lines. Okay, which model is a better predictor? Well, it kind of looks like the one that comes closer is the 13x plus 25. If we're going to predict, I would guess the purple line which the purple line was 13x plus 25. I think that's a better line. The reason, and it says defend it, because it just seems like it goes a little better with our, it's kind of in the middle here, and then it goes up to that really weird number that when we go way off. Okay, so anyway, let's go to the next page. So this next thing we're going to talk about is what's called the line of best fit. And I'll tell you right now, line of best fit has changed from when I was in school, even when I first started teaching. Line of best fit would have been the trend line. So we've been doing trend lines is what we call them now, but back then it would have been called line of best fit. The reason for that is because we can use computers now. And so in order to find the line of best fit, we're going to do what's called a linear regression. And let me show you on that next slide what that means. So a linear regression is a method used to calculate the line of best fit. It is done with computers and calculators. We're going to do it with Desmos here in just a bit. So a line of best fit is a trend line that most closely matches. And again, back in the old days, we would have just kept them closer and closer, but now we can use a computer. So that's what we're going to do right now. We're going to take this data and we're going to enter it in to Desmos. So go to Desmos. If you're watching from home, you can just click on this and it will take us there, hopefully. And let's see if it's going to go. If not, just go to desmos.com/calculator. Okay, so just ignore what I have right there and ignore that. So now what we're going to do is we're going to make a table. So we're going to go up here to the plus sign. We're going to go down to table, and then we're going to enter in these numbers. So x is 1 and y, is 30. I'm just clicking on every box, and then I have a 2 and a 55 and a 5 and a 75, 8, and you have a keyboard. You could actually just type these in if you wanted to. 9, 145, and 17, and 250. Okay, now your graph would have looked like this. When I first did it the first time, my graph, I had it really close in like this. And so it didn't show up, and I was like, oh, man, where's my graph? So you have to go out. Oh, I'm going to change that color. So I'm going to go up here to the gearbox. I'm going to change that color to red because I want it to show up a little better. Okay, so this is what our line looks like. It's obviously a positive correlation. It almost looks like a vertical line. Okay, but don't worry about that. It still will do what we need to. So what we're going to do is the linear regression. And again, we weren't able to do this until graphing calculators and computers came along. So it's pretty awesome. So we're going to go up to the plus sign. We're going to click on f of x expression, and we're going to enter in what our line regression is going to look like. So we go y sub 1. It is just slope-intercept form, just with a few technicalities. Here's one of them. If I'm doing a regression, I have to use a special symbol. Line of regression, see where the B is on your keyboard. Go below that, and that little tilde, if you're in Spanish class, a tilde sign, but it's that wavy line. So right down here, I'm going to kind of try to see if it'll make it more obvious. I'm going to click on that. Then I have to go slope times x sub 1. Oops, go back to x sub 1. And then plus, and I have to go back up and pick up a b. Okay, and this is what my line is looking like. And that is a best fit line. And look how close that is. See, we can't do that. The computer can do it for us, so it's awesome. Now, some of this other stuff that is on here, you're going to notice, is we're going to come back to. What I want you to look at is look in that top left-hand corner. You see statistics. Move down to where it says parameters, and it tells you what M is, 13.5588. And B is 17.5882. They go out to 4 decimal places. That's how exact they are. We're just going to kind of round it and probably do 13.6 and 17.6 when we write the equation, okay? Leave that there. We're going to come back to it. So we're going to take that information we just had, and we're going to write our equation. Y equals 13.6 plus 17.6. So that is as exact as we're going to be. We're not going to be any more exact. That would be our equation for a linear regression. Now, you won't have to do this for the test, but it will come up at a later time. You'll probably do it with a graphing calculator the next time you do it, but I just wanted you to see what was happening with it. Now we're about ready to do another one, and you're going to actually try it, but I want to talk to you about this letter R up here. See how R is 0.9955? That's going to be our correlation coefficient. We're going to talk about that in just a second. So just to let you know, but I want you to try doing a linear regression on your own. But that is what we're going to concentrate on in just a bit. Okay, go back. Now on this next one, you're going to try it, and you're going to go back to Desmos, and you're going to enter this in for your table, and that is in your book, so that will be lots easier. I'm going to go do it too, and then we're going to compare our lines. Make sure when you go back to Desmos that you actually write it out. Now when we enter the table, this program is using, this book is using a graphing calculator. We will put an M there. B will still be the same, but they use an A because that's what a graphing calculator looks like. Okay, so go out to Desmos right now and graph this table. So we're going to go out to Desmos. We're going to clear out what we have there, and we're going to enter it again. So again, you go up to the top left-hand corner, go to table, and we're going to enter all those values in. Go. Okay, I put on my table, and I've entered all those values, and look at my graph. Well, that's not too helpful. So I'm going to actually pull it out a little bit. Ooh, look at that weird one way up there. Did I do something wrong? 1 in 54. Ah, I did. Look at that. And that was, look, I did a couple things wrong. Correct those. So that should be 5.4. I wondered why it was so weird. And 6.1. Double check my table. Let's see if I did it right now. 10.3, 10.9. Yeah. Okay. So this just gives us a little better idea of what our graph would look like. Okay. So now we're going to get that linear regression, obviously a positive correlation. These aren't always going to be positive correlations. Just these two were. Okay. So you can have a negative correlation and still do a line of regression. Okay, so now let's go out and do that line of regression. Go to the plus sign, go to f of x. Remember how we enter this. This is y sub 1, and that's how we do it. Luckily, it just does it for us. And then we have to go to the tilde out here. I have the ABC, and we're going to click that. And then it is m x sub 1 plus b. And that gives us our line. Okay, so it gives us a slope of 0.77 under parameters. Look underneath parameters where it says m is equal to 0.776823. Wow, that one went way out. And b is 4.6902. We're just going to go 2 decimal places. So how about, but look at that. That's 0.77. We're going to use 0.78. And so our slope is 0.78. And our y-intercept, I'm going to write this down. You might want to write it in your book too. So slope is equal to 0.78 and y-intercept is 4.69. Okay, we're going to go put that back in our book and then leave that one there. Don't take that one away because this one's going to give us a lot of data later on that we're going to use. Okay, so let's go back to Lumio. So when I say back to Lumio, I just mean back to the program. You're not doing anything. It's not going to look any different. Okay, so now we're going to write that equation. So you wrote down your m, and we found out that m, we are using 2 decimal places, so 0.78, and we chose b to be 4.69 is what we used. Okay, I don't know what all this stuff over here for. That's probably, if we did it on a graphing calculator, I don't know, but we're not going to do that. Okay, so we get y, and then our line of regression is going to be 0.78x plus 4.69. Okay, that's our equation. So I know it's a lot of work just to get an equation, but that is the most accurate. That's the reason it's called line of best fit. Again, that won't be on your test, but it will be in your future, so it doesn't hurt to learn it. So what will be on your test is this. This is the next example, or I'm not sure where it is in your book, but here's what you're going to want to do. If there's not space for your book in it, you're going to want to write down what a correlation coefficient is. Okay, so right here, correlation coefficient. You're going to want to write that down. And what is a correlation coefficient? Well, first off, it's represented by R, and it is a number between -1 and 1 that indicates the direction and the strength of the line. What is the strength of the line between the two quantities? Now, that's your first one. Correlation coefficient is R. It's a number between -1 and 1 that indicates the direction and strength of the linear relationship. Okay, you can just stop at linear relationship. Okay, so write that down. Correlation coefficient represented by R is a number between -1 and 1 that indicates the direction and strength of a linear relationship. The next definition is dealing with what's called bivariate data. Okay, bivariate data, you've been using it, but it's a set of data that uses 2 variables. Well, we're going to do a lot of bivariate data set because it's going to be between two variables a lot of times. We're not always going to talk about it as a data set. Sometimes we're just going to talk about an equation. Okay, now in that column in your book, you're going to want these next slides too. So we're going to go to the next slide because right down here it says when the correlation coefficient is close to 1, what happens? Well, I would click on that point right there, but you can see it won't do anything. So it's in the next slide. So when you click on all of them, when the correlation coefficient is close to 1, and so when I say close to 1, I mean like 0.99, that's really close to 1. 0.8 is going to be a little less, 0.7 a little less, okay, it gets weaker. So notice there's a strong positive correlation between the two variables. As the value increases, so does the y value. So this has, right here, it's saying R, the correlation coefficient is 0.984. So that's really close. And what that means, this is what you need to write down. There is a strong positive correlation. It is a strong positive correlation between the two variables. So this is strong positive, okay? So when we look, and then when we go to the next one, we look at this graph, you can see that's pretty weak because there's hardly any association. But if I'm going to draw a line right here, okay, it's still not going to be too strong. So this means my correlation coefficient is close to 0. Okay, so anything 0.3, point like 1, 0.2, 0.3, we can even go negative, negative 0.1, negative 0.2, negative 0.3. Those are all weak correlations. Okay, those are weak correlations because they're so close to 0. Then when we go out here and we have our next one, when it is close to a negative 1, notice the line changes to go negative. It's a negative correlation, and it's strong though if it is close to negative 1. So negative 0.99, negative 0.9, negative 0.8, negative 0.7. You can see how it kind of dwindles off. And if I was at a negative 0.7, if I were making an approximation, your line would kind of still be here, but not nearly as close as what that is. So that's what a correlation coefficient is. How close is your line of best fit to the data that is given? So we're going to go out to Desmos right now and look at that last line we have. So if you look underneath statistics, don't worry about the R squared right now. Don't even have to worry about that. Look at R. That's a 0.9972. That's a pretty accurate line. And look at how good that line is. That's a pretty strong line. So that's the reason our correlation coefficient is so high. Okay? So now we're going to try these in books. And this is what you want to realize. Your correlation coefficient is going to go from negative 1, whoops, that's an R, to 1. That's what R will be between. So it's going to have a negative correlation here. It's going to have a positive here. The closer it gets to 1 is going to be as strong. Okay? Closer it gets to negative 1 can also be strong. It is only weak. It is only weak when it gets in here. This is where it's going to be weak. Okay? If it's a decimal closer to 0. Okay, so look at number 1, number 2, A and B. Do those. Go. Okay, so on 1, this is 0.1, not 0.99. That's pretty darn close to 0. Close to 0, this is going to be a weak. This is weak. It's a weak positive correlation because it is so close to 0. Okay, now I have a negative 0.6. It's not really strong or weak. And we would actually say that this is a negative correlation that is not strong or weak. And if we were doing comparisons, okay, let's say that we needed to do a comparison here, and they would go, okay, let's compare. Well, if R is negative 6, which one is stronger between R being negative 6 and R being negative 0.8? Which one's stronger? Well, R being closer to negative 1, this one's stronger. That's the reason this one's kind of wishy-washy. It's not really strong or weak. Okay, good. This is something that shows up in your EOC test is correlation coefficient. So this is a correlation coefficient. How strong is that line of best fit? Or for you, how strong is your trend line? Because we won't do linear regressions all the time. Okay, next thing we're going to talk about is what's residuals. A residual is the difference. So we're going to write this in that left-hand column of your book. A residual is the difference, let's go with lavender, the difference between the y value of a data point and the corresponding y value from the line of best fit. Okay, this right here is the most important thing you have to understand. A residual, you find it by taking the actual y value minus the predicted y value. That's how you're going to find out what your residuals are. And what will happen is that you'll have a table of values, and you'll have like your x, and you'll have your y. That's a y. That's a y. I got to erase that. That's too messy. That's a y value. Okay, and then you would have another table over here, you would have another line over here that talks about what is your residual. Okay, and you would then go, you would subtract. No, actually, sorry, this would be your predicted y. And then you would talk about what is your residual. Okay. To find your predicted y, you have to actually plug it in to the line of best fit. So we would come up with an equation. We would take our different y, we would plug in our x values, come up with our y values. And I'll show you in just a second what we're going to do. Then we subtract. This is going to be, this column right here is you take y minus predicted y. Okay, using our equation that we would come up with. Now, a residual plot shows how well a linear model fits the data set. If the residuals are randomly distributed on either side of the x-axis and cluster close to the x-axis, then the linear model is a good fit. So this one doesn't make a lot of sense, but go back out to your Desmos. Okay, and what we're going to do here is we're going to find out the residuals. In order to do that, see where it says residuals up here? Hit that plot. So see where it says residuals. I wish I could somehow show that to you. Hit plot. And then what you do is you make your graph, you look at your graph down here, and I want that to be a different color so that, whoops, so that you can see it a little better. We're going to make that an orange. Okay, now look at your orange. See how close that is around your x-axis? That means that line of best fit is really good because your residuals come up down here. Now these we don't talk about whether correlation or anything because they're going to just go right around that x-axis. So that's what's really handy. And how they found these was subtracting the original y by the predicted y value using the equation. Okay, back to our note. So on this one, this is not in yours, I realize that, but I'm going to show you what's happening on it, and then we get to try one together. Okay, so if I look at this, I'm going to move this up a little bit so I have some room to work. It won't let me. Okay, so what's going to happen is that these y values are what really happened. These are the y values that really happened. What we're going to do is we're going to come up with predicted y's. To do that, you take the equation that is given and you plug in the x values. So I'm going to make a table right here. Okay, I'm going to make a new table. And I'm going to take my x values of 0, 1, 2, 3, and I'm going to show you what's really happening. So I'm going to take negative 35x plus 1208. And then I'm going to come up with my predicted y. This is my predicted y. Predicted. That's what's going to go in this column right here. And we could just send it right over there. So what we're doing is we're going to take our x values and we're going to plug those in to our line of best fit that we would have gotten by using a linear regression. And I'm going to plug all those values in and come up with it. Well, that's just going to give me 1208. That's my predicted value. Now I'm going to take negative 35 times 1 plus 1208. And then I'm going to do it for each one of those values. Yeah, it's a little tedious. Okay, so that's the reason we're going to do this off screen. Okay, and I'm just going to come back and show you these values. And then we're going to go from there. Okay, so I've done all the predicted values. And all I did was plug into my calculator what you're seeing over here. Okay, and I just plugged in this value right here. And then I just plugged it into my calculator and then I wrote it down. So feel free to pause yours right now. Write those values down because we're going to be using them to find the residual. We have to use that. So I'm going to erase this so I have some space to work. And we're going to then, so while you're copying down, I'm just going to do this. Okay, so now what we're going to do is we're going to take and subtract these two values. And that's going to give us what our residual is. You're wondering, where the heck am I going to use this? This is what they use to predict trends in the business world and in any part of our world. This is what they use to predict it. Okay? And there are people out there making big monies doing this right here. So what we're going to do is we're going to subtract 1235 minus 1208. We're going to sometimes get positive numbers. Sometimes we're going to get negative numbers. So 1235, and we always have to take actual minus predicted. On my first one, I am taking 1235 minus 1208. And I'm going to take my calculator and subtract that. And I get 27. Then I'm going to take 1178 minus 1173. Okay, and I'm subtracting all of these values to find out how close this is. This is going to tell me how close on that particular point I am. Okay, and then we're going to do 1115 minus 1138. And we're going to get a negative 23. So you can see this is where, when we were looking at our graph, it's going to go above. And so if here's my x-axis, see how this one's 27 above. This one's 5 above. This one's negative 23 below. So it's still clustering right around the x-axis. So that's a good line, but it's just going to go off a little. Okay. So do the subtractions, all of these, finish that up, go. So we can see what our residuals are right here. Okay. It tells us what our residuals are. How close were we every point of the way? So you can see on this one right here, we're kind of pretty far off. But we're pretty close. We're really close on this one right here. We're only -1. So each point is going to be a little off. And then what we could do, because we have computers, we could maybe work on that line to get closer and closer and try it again and do some other things. And you know, with some of these high-powered computers, it would do that. Okay, so these are the values. I'm going to go to the next screen because if you couldn't read my handwriting, pause it right here and take down that. And then pause it right here and take down that information. Same information I just gave you, but it just gives it a little clearer. And you can read it better. So pause whenever you need to write those down. So this is where it shows plotting the residual for each x value. If this is my line of fit, if this is my line of best fit, using my linear regression, these would be my plots. How far off am I? Okay, and that's what it's showing us. Notice this is the number of students. We don't label this because it's a residual plot. Now, the scatter plot with the line of best fit suggests there's a negative correlation. Yes, the residual plot does not randomly distributes above and below and closer. So the linear model is a good fit. That shows that. But we don't talk about the correlation of a residual plot. That's just not what a residual plot does. Okay, but we will use that. Okay. Here's an example that I think is in your book. And they gave us the line of best fit. They already did the linear regression. They came up with our line right here. Then what we would do is we would have to find out what are those predicted values. So right here, we would find out the predicted y values, and then we would find out the residual. That is something that we're going to ask you to do on the test. We're not going to have such big numbers, but we would ask you to find out the predicted values and then the residuals. Okay, so you'd have to refer to the other table. I'm going to stop there for today because that's a lot of information, and we'll continue the next day to finish this lesson up. Thank you.